Greetings, physicists. This video is going to be about static equilibrium, and also we'll get on to the end towards stability and balance and things. So, we're going to start with an object, round object like this, and I'll put some dots on it. You'll see why in a sec. We're going to move that object from here to here, and it will be like this. And we're going to say that those dots don't ever change, that at every point along that motion the dots were in the same exact position. When we do this, we say that this object is undergoing translational motion. And I should probably put a number line on here that, like, the object, this is like meters, right? And the object started at 1 meter, 2, 3, 4, 5, 6, 7, 8, and ended at like 8 meters. This is position in meters. So the object did move relative to its starting point. All right, so we'll call that pure translational motion. Now let's draw the same object, and let's put it at, right, we'll put it right at 1 meter to start with. And then let's claim that this happens. The secondary condition is this. Okay, so it's still at 1 meter, which is where it started. But look at the dots. The dots have changed. So this is an object that rotated. It did not translate. So we'll call this rotational motion. It didn't go left or right. It just spun. And we've looked individually at both types of motion, and if you did rolling motion, right, we had a combination of those at the same time, where there was the number line from 1 meter up to 8 meters, and the thing started here, and the thing ended here, so it was spinning and translating at the same time. That was all for objects that are moving. Now we're going to talk about the idea that object stays at the same position and doesn't rotate at the same time. So it does neither of those types of motions at all. Or we could also say that it stays in one spot but does not get faster. So if it was going this fast and it is still going that fast at the second time and it hasn't translated left and right, that is also going to be considered a static equilibrium. So let's make a definition. A static equilibrium. And I realize I just tried to define it in terms of position, but really it has more to do with acceleration, that the movement is constant. So a static equilibrium object is not accelerating, which means that the forces on it are balanced. Sigma F equals 0, and delta V is also equal to 0. There's no change in velocity. It could not be moving, but it could also just be moving at a constant speed. But that's only one condition. So condition 1, the forces are balanced, the linear acceleration is 0. Condition 2, that there will not be any net torque on the object. So the delta omega is 0. So there's no angular acceleration alpha. And that can look like a couple of things. But most commonly, what you will see with static equilibrium problems is non-moving objects like buildings. Static equilibrium is used by engineers all the time when they have to build stuff. So we'll use things like, a very common one are signs. So like you have a big building, right? And then they put a sign out. So there'll be a rope going off the edge, and then the sign will be held up by that rope. And the sign is pushing up against the side of the building here, and there's a tension in the rope. And so the sign doesn't move up and down, so the upward forces and the downward forces and the left and right forces have to all be equal. because the sign doesn't move, but it also doesn't swing back and forth, so the torque in the clockwise direction and the torque in the counterclockwise direction also have to be equal to each other. And all those things happen at the same time. So we wind up solving a bunch of different equations to figure this stuff out. So I'm going to just start with a quick example of a balance beam to kind of illustrate this. So let's say we have a balance beam. No, let's not make it a balance beam. Let's make it a hanging rod. So we have a string hanging on one end, a string from this end holding it up. And we'll say it's a uniform rod of mass m. And for it to be in static equilibrium, it can't have a torque, it can't be angularly accelerating, and it can't have a net force, so it can't be linearly accelerating. So I'm going to draw a free body diagram for this object. There are three forces acting on it. One acts in its middle, one acts over here, and one acts over here. So I'm going to name those three places. We'll call this position 1, position 2, position 3. And I will also call each of those forces force 1, force 2, and force 3. So force 1 goes up here, straight up. I'm just making room here because this is also going straight up. So force 3 also goes straight up. And then we have a downward force, that's gravity, and that's force 2. And if we do our sigma f for this problem, you can make either direction positive or negative, but essentially sigma f has to add up to 0, so really force 1 plus force 3 has to equal force 2. And we will find that if this is a uniform rod, then force 1 and force 3 have to be equal to each other. And you can imagine otherwise there would be a torque in one direction or the other about the pivot, about the middle anyway. So we could say that force 1 has to equal force 3, has to equal, they each have to be half of gravity. So mg over 2. Now, let's do the torque equation. Now, for the torque equation, we have to pick a pivot point. So I'm going to, and it doesn't matter where you put your pivot point. In fact, we're going to prove that it doesn't matter. So I'm going to pick some point on the rod right there, which is point X. All right, and we will show, so let's do the sigma torque then about point X. Well, if I'm looking here, we have a counterclockwise torque, no, sorry, clockwise torque at position 2. We have a counterclockwise torque at position 3. We have a clockwise torque at position 1. So 1 and 2 are working together in terms of they're causing a torque in the same direction. 3 is causing a torque in the opposite direction. So for this to remain in static equilibrium, the sigma torque will have to be 0, where the two torques going the same direction, which was torque 1 and torque 2, have to add up to torque 3. So let's plug that in. Well, torque, if you recall, was equal to F, or sorry, bad habit, don't follow that. It's equal to R cross F. So we'll do some radii here, and I'm going to, no, this way, okay. I'll draw some radii here. The first radius is from point 1 to point X, so I'll call that that distance X, and this is like X1, position 1. The second radius is from position X to position 2, so that's like X there, and that's X2. And the third radius is all the way up to position 3, so that could be position X, this could be position X3. And if I had a number line going this way, and that's like 0 all the way up to the infinity, right? Not that infinity is a thing, but let's just say it does, the positive direction is this direction. Then my final minus initial is always the right one, like x minus x1, or x2 minus x, etc. Okay. So, torque 1 would be Rf, and the radius here is x minus x1 times the force, which is mg, over 2. Okay? Plus torque 2 was x2 minus x times, that's the radius, times the force, which was just mg. Torque 2 was from gravity itself, so that's not mg over 2. Equal to, torque 3 was position 3 minus position x, and this was also an mg over 2. Notice that the mg cancels. I can just divide through by it. So what I'm really getting here, and if I distribute the 1/2, I'm getting x over 2 minus x1 over 2 plus x2 minus x equal to x3 over 2 minus x over 2. Okay, that looks good. And I'm going to do a little bit of combining like terms. So if I add x over 2 to this side, to this essentially, I'm going to get x over 2 plus x over 2, which is just x. So I will get, and these will cancel over here, and I will get x minus x1 over 2 plus x2 minus x equals x3 over 2, and look, this x minus that x goes away. And so now I can come back down here and get, so this is negative x1 over 2 plus x2 equals x3 over 2. And now I'm just going to move this to the other side, so I'll get x2 equals x1 over 2 plus x3 over 2. And you could actually say those have the same denominator, so this is going to be, as a final cleanup, position 2 equals position 1 plus position 3 over 2, which is actually an average, right? Well, let's go back to the picture so that this makes some sense to you. I realize that picture is very been written on, so we're just going to, it's too busy, we're going to draw this again. So here's the rod, here's the string here, here's the string here, here's the gravity down, right there, the mg. And that was position 2, that's position 1, and that's position 3. Well, we said that in order for this thing to be in static equilibrium, position 2, which is here, has to be the average position between x1 and x3. So it has to be essentially halfway between x1 and x3 if those forces are to be equal, which we set them equal to themselves at the beginning. And also if this is a uniform rod, where gravity is right in the center of the rod. But notice that, and what I told you would happen happened, the x's, this x was the position of the pivot point, which we arbitrarily claimed was like right here. But it canceled itself out. That x does not appear in our final equation. It doesn't matter where you put your pivot point in a static equilibrium problem. If you make the pivot point here, all the torques about that point will cancel each other out. If you make the pivot point the left end, all the torques around that point will cancel each other out. So when you're doing a static equilibrium problem and you need to calculate the torque on an object that's supposedly not accelerating, or angularly accelerating, you can make any of the points your pivot point. Whether or not they're what would be the real pivot point is not relevant. Any pivot point would do. In fact, you could even pick a point over here. There is no torque about this object rotating around the position either. So keep that in mind. That's the idea of static equilibrium. We will also talk a little bit about, extend this to something practical, which is stability. So I'm going to draw a shape standing on the ground. So this is a big plank. Gosh, I can try and draw it better than that. No guarantees though. All right, we'll call this a uniform rod standing vertically there on the ground. And since it's uniform, its center of mass will be right here. And there is some width here, and there's also some height here. So this has got dimensions. And right now, we could consider some forces, but I'm going to tilt it. I'm going to take that rod and tilt it just slightly so that the one corner is down, like this. I don't know how well I drew that, but you can see that it went through some angle. If we extend this line out here, it went through some angle theta. Now, when it's sitting still, it has a force down like this and a force spread out across its bottom, but when it's tilted up, the force is down, and then there's only one force up from down here, which is at that corner. So think about this. If I give that object a little bit more width here so you can see or like zoom in on it essentially. Yeah, well, let's put it here. If this force goes up like this, and this force goes down like this, and this is kind of the pivot point, you could almost say. But, well, let's notice a few things. If you were to hold it in place right here and let it go from an initial velocity of 0, then the up and down forces, if you were to just do a sigma f, should equal 0. The gravity down and the force up should be balanced if it's not going to accelerate up or down, or pretty close to that. But if those are equal forces, that means that the force up and the force down, right? Let's like force 1 and force 2, if we're calling it that. Here's force 1 and here's force 2. If those two would then be equal to each other, notice that it doesn't matter where I put the pivot point. If I put the pivot point somewhere between them, they both cause a clockwise torque, and this thing will fall over. If I put the pivot point on one of them, like this pivot point here, then this guy doesn't exert a torque, he has 0 torque, and this guy exerts a counterclockwise torque, so the thing still falls over. If I put the pivot point over here, then this torque, remember these forces are the same, this F2 and this F1, but this one is at a smaller radius than this one, and so this one wins, has more torque, and look at it, it's causing this thing to tip over. So any point out on this side will cause force 1 to win. And similarly, any point that I pick over here, if this is the pivot point, F1 is smaller than F2, and F2 will win and cause a torque in this direction. So no matter where I put the pivot point, this thing falls over. It is unstable. Now I'm going to, since it's so hard to draw thin objects, like I was trying to, I'm going to draw my next one a little bit wider. Let's try to do that. And I think that will work. I'm going to exaggerate just a little bit. Pretend that this force is here and this force is to the right of it slightly. And again, pretend this thing tips. Well, if I do it that way, this force looks closer to over here. This point, let's pick a pivot point. If I place the pivot point here at the bottom, this guy, this bottom guy, this force 1, will have no torque, and this other force, force 2, will cause it here. That will cause this thing to tilt back towards its center and not fall over. If I put the pivot point over here, who's farther away from that pivot point? Well, force 1 is farther away, and force 1 would cause it to tip back towards its center. If I put the pivot point over here, force 2 is farther away, and it would cause it to rotate back towards its center. So any place where I put the pivot point will cause this thing to rotate back towards its center. So essentially, if this is the center of mass, position, center of mass, and this is like the position of the pivot, this shape becomes unstable when the center of mass has moved far enough sideways so that it's past the pivot point. And once it's past the pivot point, the thing will fall over. So what are some stable, well, if you're going to think about buildings in terms of stability, if you build your building very tall and very thin, look where your center of mass is, and look how far it has to move, maybe only very small distance to get past where the pivot point would be. That's pretty small. So tall, thin objects are very easily tipped. They are very unstable. Whereas if you're building a building here, what if you had the exact opposite? What if you had this building? And the center of mass, again, is right in the middle. This building's center of mass would have to move way over here to get past this pivot point. And that would be hard to do for that shape. So a lot of stability has to do with that idea, those shapes. So whenever you see people, back when I'm old enough to remember that the SUV was kind of a car that was being developed and in my youth became a popular thing. But if you look at an SUV from the front on, like let's draw an SUV from the side. Right, they had a big, something like this. They tend to make them very tall. So when you look at them from the front, it's big, high profile. And that means the mass is up high too. So it was a very tall car, and they would warn people, don't take the curves too quickly because you'll tip over your SUV. And I don't know how often that actually happened, but it's kind of a myth. They were worried about the height of the car, and that can be a problem with Big Mac trucks and stuff that carry their mass very high. It's a big problem actually with boats. Boats are ridiculous. I mean, here's the water. And if you look at a boat's shape, it's like this. Like the bottom part is actually the thinnest, the least wide, and the top part is the most wide. I mean, you could imagine, this is an exaggeration, but what if your building were a pyramid, an upside down pyramid, where the center of mass is actually way up here? And that's the pivot point, right? The center of mass has to literally stay in line with the pivot, cannot move sideways or the thing will tilt. Cannot move sideways at all because the pivot is directly underneath it. Whereas if you have a pyramid like this, and the center of mass is down here, that's so impossible to tilt. You're never going to tilt a pyramid. I mean, you would literally have to rotate it until it looked like this before it would tilt over. So a boat is not quite as bad as a pyramid, but it's pretty bad. Now, the saving grace of the boat is that some of it's underwater, so the pivot points are here and here if it were to tip. But even so, it can do so relatively easy. And to make matters worse, I'm going to scroll here and draw this again. If you were back in the 1800s or something and you wanted to protect yourself from pirates, what did you do? So here's your sail. This is a great boat. You put a big heavy iron cannon on the deck of the boat, which is a bunch of mass. So now your boat's not even uniform. So if the center of mass had been here, by putting something high up, you're actually raising the center of mass to higher. And so, again, which is bad for stability. The higher your center of mass, you could show this with a building. If the building was tall and thin, if you place the center of mass on the top, then when you tilt angle theta, like this, right, if the center of mass had been here, and you tilt the line with the centers of mass on it, this one has moved here, but this one has moved way over here. It's moved farther per angle, right? R theta, x equal R theta. So putting the center of mass up if high is dangerous. So they would load these cannons on the top of their ships, and you're just asking for the ship to flip over, to capsize, because you've made your center of mass so high. And the cannon, of course, shoots this cannonball, and you know from momentum that if it goes here with MV, it's going to push backward with some force to get that momentum, and that just causes the ship to roll, and so ships would just roll over when they try to fire their cannon. So what they do, if you ever want to go build your own pirate ship or something, you take a whole bunch of lead bars, and you stick them in the very bottom of the ship, what they call the bilge. They just line the bottom of the ship with this really heavy metal lead, which lowers the center of mass down lower and makes it a lot harder to flip the boat. So that's the concept of stability. Does your center of mass move past your pivot point? Then you tip. Coupled with the idea that you are in static equilibrium if all your forces are balanced and if all your torques are balanced.